Okay, hi everyone. In this video, we're going to talk about periodic trends. So make sure you have your periodic table out. These are going to be trends as you move across the periodic table or down the periodic table. And when we move across, we call them periods. So there are 7 periods on the periodic table. When you move up and down, those vertical columns are called groups or families. So there are 18 groups on the periodic table and 7 periods on the periodic table. Let's start with atomic radius. This is the size of the atom, the physical size of it, like how much volume it occupies. So let's talk about as you go across a period first. To understand the size of the atom, the radius of the atom, you have to understand where the electrons are. Because remember, the nucleus, which has almost all the mass, is a teeny little spot right in the middle. What really determines the size is how those electrons are filling in around it. Now, every period or row on the periodic table represents an energy level. This is a space where the electrons fill in. Bohr called this a shell, and he had that concentric model where it's like circle, 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 circle. Schrodinger kind of helped us realize it's more like a 3-dimensional lobe sort of a shape, and we call that an energy level. So think of it as an electron region. Every period, so period 1, 2, 3, 4, up to 7, has one of these new energy levels. And all of the elements in that area, their new electrons are going to fill into that outermost energy level. As you move across a period, you have more electrons filling into the same energy level. So notice it's not making the atom bigger. Like you might think as you go across from Na through Ar, look at Na on your periodic table, number 11, look at Ar, number 18. You might think since you're adding protons, neutrons, electrons, it's going to get a little bit bigger, 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 bigger. But in fact, those electrons are filling into the same energy level. So it's not going to get bigger. And in fact, it's going to get smaller. Here's why. Since you're also adding more protons as you move across a period, you have a stronger nucleus to pull all of the electrons in closer. So the electrons are filling into the same energy level and the protons are gripping that energy level in closer. So as you move across a period, elements are actually shrinking in size. For example, let's look at sodium versus argon. So sodium is going to have 11 protons in its nucleus. Argon is going to have 18 protons in its nucleus. How do I know that? Atomic number 11, atomic number 18. Now, each of these are going to have their outermost energy levels in energy level number 3. How do I know that? Period 3. They're the 3rd row from the top. So we're going to have some elements here, electrons here in number 1, here in number 2, and here in number 3. And in fact, how many electrons are in sodium's outermost energy level? Just 1, because we know it as 1 valence electron. Now, for argon with 18 protons, we have almost twice as many protons pulling its electrons in. So these energy levels, it's still going to have 1, 2, and 3, but the stronger nucleus is able to pull its electrons in a lot closer. And here we have a full outer shell, 8 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons are going to be pulled in. So notice the size shrinks as you go across. That's probably the most counterintuitive of these trends, because you would think as the atom gets heavier, it's probably going to get bigger. Not necessarily true. But what about down a group or family? Well, every time you move down, you're adding an entire new energy level. So the size is going to greatly increase. Let's compare this argon right here, which we just drew, argon, versus the next element, which is potassium. Well, potassium, what's the big difference? Well, we have 19 protons, but this one is going to have a 4th energy level. So we're going to go 1, 2, 3, 4. We have a 4th energy level. We have 1 valence electron there in the 4th. We're going to have a much larger element. So as you move down the periodic table, down a group, we're going to have larger elements because you're adding a brand new, an entire new outermost energy level or shell to the outside. So overall, atomic radius decreases across a period and increases down a group. So with this in mind, look at your periodic table. What's the smallest element? It's not hydrogen. That's the lightest element. It's actually going to be helium. Helium has a smaller atomic radius than hydrogen because helium's 2 protons pull its electrons in closer than hydrogen's 1 proton. What about the largest element? Well, that's going to be francium. That's going to be the left side bottom element because we have 7 energy levels and that outermost electron is held very loosely around the outside. Here's an image I found online showing atomic radius. This actually shows the numbers, and this is in picometers, which is smaller than nanometers. This is 1/1,000,000th of a meter is a picometer. And you can see that what we said was true. The smallest element you see here is 31 picometers across. That's, or I guess that would be half the distance across, but that's going to be helium. The largest we see here is cesium, but that's just because they don't show period number 7. All right, on to the next trend. What about ionic radius? So ionic radius is comparing the size of an atom to its ion. For instance, oxygen versus oxide, O2 minus, or aluminum versus an aluminum ion, something like that. So comparing an atom to its element, an atom to its ion. Well, let's look at the first trend. Cover some of this up. Positive ions first. Positive ions or cations are made by removing the valence electrons. And of course, you know, valence electrons are the outermost electrons. The valence electrons are the electrons in the outermost energy level. So when you remove them, what do you think that's going to do to the size of the atom? Well, it's going to greatly shrink it. Let's look at Mg versus Mg2+. Mg, because it's in period 3, it has electrons in energy levels 1, 2, and 3. And in fact, how many valence electrons are in its outermost energy level? 2. The 2 outermost electrons are removed, so now it only has electrons in energy levels 1 and 2. So that might look something like this. If we have a regular Mg, we're going to have 12 protons. We're going to have electrons in energy level 1, energy level 2, and energy level 3. When we turn this into Mg2+, we're removing the 2 electrons in the 3rd energy level. So we still have 12 protons in the nucleus. Here's our first energy level. Here's our second energy level. And that's it. There is no more 3rd energy level anymore because those 2 valence electrons have been removed. And we can see that we shrink it down. So as you can see here, positive ions are smaller than their atoms. In all of these examples, you shrink the size of it when you go from a neutral atom to a cation. What about negative ions? Well, for negative ions or anions, electrons are added. These electrons get added to the already partially filled outermost energy level. This might make you think that anions will be the same size as their atoms, right? Like if I have, for instance, a phosphorus, a P. Let's make it simple. Let's go up N. You have 5 valence electrons, right? So here's N. We're going to have a total of 7 protons. We're going to have electrons in the first energy level and 5 electrons in the second energy level. 1, 2, 3, 4, 5. Now, when this turns into N3-, a nitride ion, you might think that those 3 are just going to fill in 1, 2, 3, and that'll be that. But in reality, those 3 electrons are going to experience electron-electron repulsion with the 5 that are already there. It would be like if you have a house with 5 kids and all of a sudden you adopt 3 more, you're going to need a bigger house. You're going to have to push those walls out a little bit. So in this case, we're still going to have 7 protons. We're still going to have, here's the nucleus there. I should have shown this as the nucleus. We're still going to have 2 energy levels, but because that second energy level is now full, it's going to spread out a little bit to make room for all 8 of these electrons. So that's kind of summed up here. There is electron-electron repulsion happening as the new electrons are added. The new electrons are repelled by the pre-existing electron, causing all of them to shift and spread out. So the trend here is that negative ions are larger than their atoms. Notice when you go from O to O2 minus, much larger. F to F minus, much larger. And you can see that trend applies. Okay. So that covers two trends. The third trend we're going to talk about is something called ionization energy. This is the energy required to remove an electron from an element. Now think about this. At least in my classes, I like to kind of personify these elements and give them kind of human characteristics. I'll say things like, this element wants to give away its valence electrons, or this element wants to gain more valence electrons, or this element has exactly what it needs and it doesn't want any more. Well, in reality, even if an element wants to give away its electrons, it still takes some energy to remove them because the electrons are locked in orbit around the nucleus. So think about it this way. What are the elements that, as I say, want to get rid of their electrons? Well, that's going to be the metals on the left side of the periodic table. Metals are always looking to lose the outermost electrons because they're more stable without them. So if I like to say they're more willing to lose, what that really means is it takes less energy to lose them. The ionization energy is going to be lower for metals on the left side of the periodic table. What are some elements that want to hold on to their electrons? Well, that's going to be the nonmetals on the right side of the periodic table, and not just the noble gases, even things like N, O, F, and the ones below those. You know, if you have 6 valence electrons, like oxygen or sulfur, you want to hold on to your 6 and gain 2 more. So it's going to take a lot more energy to remove those electrons. So that's going to be a higher ionization energy. So I kind of said this here, which elements will have low ionization? It's going to be the elements that want to lose electrons. Which elements will have high ionization energy? The elements that want to keep their electrons. So ionization energy is going to increase as you move across a period. So from left to right, it's going to take more energy to remove the electrons from the elements. And we often talk about how the alkali metals on the far left are the most reactive metals because they're so close to losing that one valence electron and being stable that the way I say it is they'll give it to anyone. I mean, something like sodium, if you put it in water, it's going to try to give that electron to the water, producing hydrogen gas and actually kind of lighting on fire in the water there. So again, ionization energy is going to increase across a period from left to right. Well, what about from the top down? Elements in the same group have the same goal in life, right? That's what phrase I like to use. By goal in life, I mean what they're always trying to do, either gaining or losing the same number of electrons. So is the ionization energy going to be the same going down? Specifically, look at the alkali metals. They all want to lose one valence electron. Does that mean ionization energy is going to be the same? Or what about the halogens? They're all trying to gain one valence electron. So is their ionization energy going to be the same? It is not. Here's what's going on there. What's important here is distance from the nucleus. For instance, lithium and cesium, find them both on your periodic table. They're both holding on to one valence electron, a single electron in the outermost energy level. Now, if I could personify these, what are they both trying to do? They're both trying to lose it, but in reality, they can't just let it go. Something has to take it, and it has to use a little bit of energy to take it. Let's look at the sizes here. Lithium has a little nucleus here, 3 protons, and where is its valence electron? Which energy level? Well, which period is lithium in? 2. So here's the first energy level, here's the second energy level, here's the one valence electron it's trying to lose. Let's look at cesium. Cesium has a much larger nucleus, 55 protons. I'll show a bigger plus here. And where is its one valence electron? Well, that's going to be in energy level 6. How do I know that? Because it's in period 6. So we have electrons here. 1, 2, 3, 4, 5, 6. Here's cesium's valence electron. Now, if you're on a quest to steal a valence electron, which of these do you think is easier for you to steal? It's going to be this one. It's so far from the nucleus it's trying to hold it. Compare that to this one, which is really close. Distance from the nucleus matters. This is when you're going down a group on the periodic table. Distance from the nucleus matters. So I kind of sum this up here. If you're trying to steal an electron, which do you think would be easier to steal? The one further from the nucleus. But wait, isn't cesium's nucleus much stronger than lithium's? With 55 protons versus just 3? Yes. But distance from the nucleus matters more than the strength of the nucleus. So even though this is a more powerful nucleus, and this is a much smaller one, distance matters more. So which of these is going to have a lower ionization energy? In other words, which is going to require less energy to remove the electron? It's going to be cesium. So lithium is going to have a higher ionization energy than cesium. So the trend is as you go down the group, we're going to see ionization energy increase. So you can see that right here. Ionization energy increases across a period and decreases down a group. Now this cuts out a lot of the elements in the middle just to give kind of a good understanding of what we call the main group elements. And the trend applies. See how we are seeing drops here, 520, 496, and so on. This image, I believe, shows kilojoules per mole. So, if you have a mole of potassium atoms, you're going to take 419 kilojoules of energy to turn that into a mole of potassium ions, and so on. So with this in mind, look on your full periodic table. What's going to have the highest ionization energy of all? Helium. What's going to have the lowest of all? Francium. Notice how those were our two extremes before? It applies. Helium and francium. So in other words, francium's outermost electron is the easiest one to steal on the entire periodic table. Helium's electron is the hardest one to steal. Hopefully I didn't missay that before. Francium is the easiest, helium is the hardest. Now, everything we just saw in this is really called the first ionization energy. This is the energy needed to remove just the first valence electron. There's also second ionization energy, third ionization energy, and so on. And we can see some interesting patterns. What are some elements that will have a relatively low first ionization energy, but a relatively high second? Think about it this way. Which element would love to lose exactly one electron, but does not want to lose two? Well, that's going to be your alkali metals, something like potassium or rubidium. So with these, you're going to see a very low first ionization energy to remove that first one, but then they're done, they're happy. They don't want to lose a second one. So you're going to see a very high second ionization energy. What about a relatively low first and second, but a high third? Well, that would be your alkaline earth metals, these ones right here, because they want to lose two, but then they're done. They don't want to lose three. So you can notice trends in ionization energies like this. Notice how something like sodium is going to have a relatively low first one. In fact, that looks like the smallest number on the entire grid here, but a very high second one, a huge jump. Here for magnesium, we see relatively low first and second, but a big jump up to the third. Aluminum, 3 relatively low ones, and then a huge jump to the fourth. So that trend makes sense, and you should be able to explain that trend there. The last trend, fourth and final one, is called electronegativity. This is a measure of an element's ability to attract a new electron. So before I reveal anything else here, just think about it. Which elements want to attract new electrons? Think about it. Hopefully you're saying things like halogens or the oxygen group. It's going to be the non-metals on the right side of the periodic table, but not the noble gases, right? The noble gases are done. So it's measured on a scale up to 4.0. So think which elements want to attract new electrons, which don't. The ones that want them are going to be elements like your non-metals here that have a almost complete valence shell or energy level, but not quite complete. Things like N, O, F, P, S, Cl, all of your halogens, things like that, but not the noble gases. And what about the metals on the left side? Do those want to attract new electrons? Of course not. They want to lose theirs. So we're going to see the highest values almost all the way to the right. Just to the left of the noble gases, we're going to see the highest values. So electronegativity increases across a period, except for noble gases. We generally don't even consider noble gases when looking at electronegativity because they just don't want electrons at all. So it's usually left off the grid. Sometimes it's on the grid, but it'll have a relatively low value. But what about down a group? Would it be the same since they all have the same goal in life? Remember I said before, like all the halogens want to gain 1 electron. So are they all going to have the same electronegativity? No. And what was the answer before for why it's different? Distance from the nucleus, same here. Distance from the nucleus. Consider fluorine and iodine. Here's fluorine. We have 9 protons. Here's iodine. We have 53 protons, so a bigger, stronger nucleus. Fluorine has electrons in the first 2 energy levels, right? 1, 2. Iodine has electrons in the first 5 energy levels. 1, 2, 3, 4, 5. How do I know that? The periods they're in. Now, each of these have 7 valence electrons here and 1 open space. 7 electrons, 1, 2, 3, 4, 5, 6, 7, and 1 open space. Now, the question is, which of these will have an easier time filling the open space? The answer is going to be fluorine. Why? Because distance from the nucleus. Fluorine's nucleus is trying to attract 1 valence electron to fill this spot, which is pretty darn close to its nucleus. Iodine, despite having a much more powerful nucleus, has a longer distance to try to attract, so it's going to be less effective. For this reason, electronegativity is going to decrease as you move down a group. This just sums it all up here. I'm going to move on from this. So you can see in this infographic here, the noble gases have been left off because we generally don't consider them. Electronegativity is going to increase across a period and decrease down a group. So what's the most electronegative element? Fluorine. Fluorine is the 4.0 GPa of the periodic table. It has an electronegativity of 4.0. It's the highest one. What about the least electronegative element? Well, that's going to be the far left bottom element, which is francium. So think of the 2 Fs as having the 2 extreme electronegativities. Francium is going to have the lowest, meaning it wants to attract new electrons the least, which makes sense, right? Because what does francium want to do? Well, it wants to dump its valence electron off onto anything it can. It doesn't want to attract new ones. And fluorine is going to have the highest because what does it want to do? It wants to attract new electrons to a spot that's really close to its nucleus. So this is why fluorine is going to have a very high electronegativity. And that does it for the trends. So make sure you review this, review the trends, and ask your chem teacher if you have any questions. Good luck.